The data is coming from global climate modeling, and this is where scientists are using computer simulations to conduct experiments and test hypotheses about climate change. These are done by simulating global weather in the atmosphere, ocean, land surface, and cryosphere. By chopping everything up into three-dimensional grid cells like here. So we see here a three-dimensional grid cell of a section of the atmosphere might look like this here to the right, where inside there is an assumption about what's going on with the clouds, if there's precipitation or not, and what form that precipitation takes. The model also connects all of the aspects of the Earth system and has models for feedback between these different systems. There's a lot of science that goes on here, but that things that science definitely knows, but there are a lot of things that scientists are still working on, and clouds is technically one of them. So back in 2010, the Intergovernmental Panel on Climate Change, or the IPCC, created a project called CMIP-5 to create an ensemble of future climate projections. And this is where global climate models were run by modeling centers all over the world from many different countries. Here you can see all those different models and which country they were coming from. To create an ensemble of future climate projections. And in total, I think there were over 40 different models that contributed to this project. And for the data in the toolbox, we utilized 20 of them that supplied daily data of temperature, precipitation, humidity, wind, and radiation. And then each model ran the same climate experiment or simulation of global weather for a historical and a future time period. So for the historical time period, the simulations started at some pre-industrial initial conditions of greenhouse gas emissions, and we extracted 1950 to 2005 from these historical simulations. From the future simulations, each model simulated an emission pathway to obtain certain levels of radiative forcing by 2100, and that's what these are. And these are the RCP pathways that you'll see in the tools that actually. And RCP 8.5 is a high emission scenario. It is the business as usual extension of our current emissions pathway, where when we start here at like 2010 actually is when they started these experiments, there was a radiative forcing of almost 2 watts per square meter. And that's as if the greenhouse gas effect is the same as shining a 2-watt light bulb over a square meter of the Earth. And then the pathway for the RCP 8.5 is as if our greenhouse gas emissions change so that the radiation from the sun by 2100 feels like 8.5 watts per square meter. It feels like an 8.5 watt light bulb shining on a square meter. And so they have an RCP 8.5 pathway that they simulated. That's business as usual emission generation. And then they also had an RCP 4.5 low emissions, which meant that by 2100, it's a 4.5 watt light bulb shining on a square meter. So they ran these experiments, and the goal, and so this low emission scenario is where there's a slowdown around 2050 and a leveling out of the radiation, where this represents a pathway of global mitigation of emissions and working together. And then for perspective, the goal of the Paris climate agreements is to not exceed a change of 2 degrees Celsius in global average temperature. Fits just a little bit here above the 2.6 RCP 2.6 basically. So it would be in here. So what our path is well above the Paris Agreement is what I'm trying to say. So then the outputs from the global climate models come out on roughly 200 by 200 mile grid cells. It looks like this. That mid-mean for like a state like Oregon, there's probably like 20 grid cells for all of Oregon here. But there are a lot of differences in climate within a 200-mile grid cell over the complex topography in parts of Oregon. So there's just a real need for finer resolution climate projections. And as with all the models, the average temperature on these grid cells coming out of the global climate models is not likely to match average temperatures we see on the ground. So to correct these errors and to increase the resolution of the data, we apply statistical downscaling methods using the same gridded observations from the historical data to correct biases in the models. And basically what we do is we do a fancy interpolation. So you can see we go from here to here. And we do that using the statistics from the GridMet climate data. Yeah, and that gets us down to 2.5 square mile grid. So we went from 200 to 2.5. And then this corrects model biases and also makes a finer resolution data set. And we did this, we performed this downscaling of global climate models for 20 of the global climate models and 2 future greenhouse gas scenarios, RCP 4.5 and 8.5. And we did this over the whole contiguous USA on 2.5 mile grid cells using the MACA method. And then we also partnered with the University of Washington, and they ran the VIC hydrology model to create hydrology outputs, and also routed the hydrology into streams so that they could simulate stream flows as well. So you'll see we have stream flow data. Okay, that's pretty good. And the result is that in the toolbox, we just have lots of different data. We have these raw climate data. We have raw hydrology data. And then we also use these climate and hydrology data to create, with simple models, some other metrics, derived metrics that could be used to monitor agriculture, fire danger. For example, with agriculture, we computed growing degree days using the temperature data. Or we computed the cold hardiness zones. For fire danger, using these different metrics, so these raw metrics, we ran the data through a fire danger model and got information about future projections on vegetation dryness and the energy release component. So there's just a lot of data in the toolbox.